Ready to see AI reimagine how images come to life? Today, we're exploring visual autoregressive modeling. Think of it like building a masterpiece, starting with broad strokes and adding details layer by layer. No more rigid grids or slow diffusion. This approach flows smoothly from fuzzy to fine. We'll talk scaling laws, zero-shot creativity, and how this method shakes up traditional image generation. Let's unpack the ideas and have some fun along the way.
In this work, the authors introduce a new approach to generating images using a visual autoregressive method. They call it next scale prediction, and they demonstrate it with examples like a husky dog image, volcanic eruptions, and rockets. Notice how these visuals differ in complexity and level of detail. The core idea here is to generate images starting from a rough version and then refining the details step by step. They also invite you to check out an online demo and their GitHub repository. This openness makes it easier to see how their method really works. At this point, they are just teasing the main idea, showing that the method can produce realistic images, from simple objects to dynamic scenes, all by working in a multi-scale fashion. Ready to dive into the specifics? Let's move on. Here, they formally present their idea: visual autoregressive modeling. We will refer to it as VAR from now on. Think of it like a transformer-based image generator that, instead of doing next token predictions like language models, does next scale predictions. The method builds images from coarse levels of resolution to finer ones, much like how we might first sketch a broad scene and then fill in details. They show that VAR significantly improves image generation benchmarks. On ImageNet 256 by 256, it brings the Frechet Inception Distance Score, also known as FID, a metric used to measure the quality of generated images by comparing their statistics to real images, down from 18.65 to about 1.73, and is also about 20 times faster than diffusion models. Compared to models like DIT, the diffusion transformer, VAR not only produces better images, but does so more efficiently and at larger scales. Interestingly, VAR follows scaling laws similar to large language models. As you give it more data and parameters, it improves in a predictable way. It also does well at zero-shot generalization tasks, such as inpainting or outpainting an image without fine-tuning. This suggests VAR could be a unified approach for various image generation needs. Now let's consider how autoregressive generation is usually approached. When I mention AR later, I'm just talking about autoregressives. In text, GPT-like models predict one word at a time, left to right. In images, the older AR methods tried to do something similar, predict pixels row by row, but that's slow and doesn't scale well to high resolutions. Look at Figure 2 here. Traditional AR image models read pixels like text, one after another, which is inefficient. The VAR model, on the other hand, introduces next scale prediction. Instead of going pixel by pixel, it generates a low-resolution image first, then refines it into a higher resolution version, and so on. This allows parallel processing at each scale and makes the whole process more efficient. The key is a multi-scale VQVAE, which helps represent the image at different resolutions as discrete tokens. By handling the image in a coarse-to-fine manner, VAR can speed things up dramatically, making large-scale image generation more practical. Why do this coarse-to-fine approach? Flattening an image into a single token sequence, like text, isn't natural for visual data. It's too slow and hard to scale. Humans don't understand images one pixel at a time. We see the big picture first, then focus on details. VAR uses the same intuition. If you check out Figure 3, you can see how VAR's multi-scale process leads to both faster generation and better results. VAR shows improved performance on ImageNet 256 by 256, with fewer parameters than competing models. It even beats larger models like LDIT in quality and speed. By redefining the order of generation from entire coarse maps to finer ones, VAR avoids the pitfalls of pixel-by-pixel generation. It makes image synthesis more efficient, and as we'll see, it also opens doors to better scaling and generalization. So how is VAR actually implemented? It uses GPT-2-like transformers, but applies them to visual tokens arranged in multiple scales. On ImageNet 256 by 256, VAR achieves an impressive FID of 1.73 and an inception score of 350.2, outperforming methods like diffusion transformer. It's also about 20 times faster. Another key point is that VAR models follow predictable scaling laws, just like large language models do. When you increase model size, data, or computation, performance improves in a reliable, mathematical way. In summary, their contributions are clear. They introduce a multi-scale AR framework, show that it follows established scaling laws, outperforms strong diffusion models, and provide an open-source toolkit. Let's move on to see how this relates to generalization and how VAR compares to other visual generation approaches. Next, consider zero-shot generalization. Ever heard of CLIP or SAM? They set a precedent for zero-shot learning in vision tasks. Similarly, VAR performs well at new tasks without extra training. It can in-paint, out-paint, and edit images on the fly. Looking at other visual generation methods, we see two main styles: raster scan AR models and masked prediction models. Raster scan models turn images into sequences of patches and predict them one after another. Masked prediction models, like MaskGIT, use a BART-like approach to fill in missing parts. Then we have diffusion models, which incrementally refine noisy images into clearer ones. VAR stands apart by predicting entire scales at once, not just individual tokens. This sets it up as a potentially more scalable and general approach than conventional AR or diffusion methods. Now let's go deeper into the math of AR modeling for images. We start with a sequence of tokens .x, and each token depends on the previous ones. To do this with images, we first have to break the image into discrete tokens. A VQ, vector quantized, encoder converts the image into feature maps, and a quantizer assigns a code, token, to each feature vector. So the image is no longer continuous pixels. It's a set of discrete tokens that a transformer can understand. Instead of predicting pixels, VAR predicts these tokens, moving from coarse representations to finer details. This sets the stage for the next scale prediction approach. Tokenization isn't trivial. Flattening a 2D image into a 1D sequence breaks the natural spatial relationships. Neighbors that should be close in the image might end up far apart in the token sequence. This can cause three main issues. It violates some assumptions about independence, it limits generalization in certain directions, and it destroys local structure. The VAR approach addresses these problems. By predicting tokens in a multi-scale 2D format, it keeps spatial integrity and avoids the awkward flattening that traditional AR models do. This allows VAR to stay true to the image's natural structure. Generating images token by token in a long 1D sequence is expensive. Transformers have quadratic attention complexity, making it slow and hard to scale. To tackle this, VAR uses a two-stage training process. In stage 1, a multi-scale VQ autoencoder encodes the image into multiple resolutions. This creates a set of token maps, from coarse, low-resolution maps to fine, high-resolution ones. In stage 2, a transformer predicts these token maps using next-scale prediction. Instead of going one token at a time, it predicts an entire resolution level at once, given the previous coarser level. This chunk-by-chunk approach, with careful attention masking, speeds things up significantly. So how exactly does next-scale prediction work? Think of it like this. You first generate a small, low-res map of the image. Then, when you move on to the next scale, you use the previous map as the prefix. The model pays attention only to what came before, keeping a causal order but on a scale-by-scale basis. Mathematically, this is expressed as a product of conditional probabilities across scales. The crucial point is that the model can handle each scale in parallel, making it more efficient. Plus, the spatial structure is maintained since we're dealing with 2D token maps at every stage, not a flattened sequence. With VAR's multi-scale VQGAN encoder, tokens at each scale preserve correlations, so the final image comes together more naturally, both globally and locally. To implement VAR, we again have two main steps. First, In stage 1, we encode the image into multiple token maps. Each scale refines the representation, starting from a coarse version and adding details layer by layer until we reach the final resolution. Stage 2 trains a transformer that predicts these token maps in order, from coarse to fine. A causal attention mask ensures that each token can only see tokens from earlier scales, respecting the temporal order of coarse-to-fine generation. Under the hood, the tokenizer is a modified VQGAN with upsampling and downsampling operations. The transformer is a simple GPT-2 style decoder with a few tweaks like adaptive layer normalization. It avoids unnecessary complexities and still performs well. There's a formula to determine how scaling the transformer's depth affects model size and parameters. It turns out the parameter count grows with the cube of the depth, which helps predict how big the model can get. They test VAR on ImageNet with various depths, 16, 20, 24, and 30 layers, and compare it to other AR models that also rely on VQ-VAE. They try resolutions of both 256 × 256 and 512 × 512. This setup lets them directly compare VAR's scalability and efficiency, showing how it handles bigger images and deeper models, and how it measures up against previous work. Now check out Table 1 on the page in front of you. It compares different generative models on the class-conditional ImageNet 256 × 256 task. Metrics like FID and inception score help us see which models produce more realistic images. GAN-based models like BigGAN or StyleGAN-XL and diffusion models like LDIT are in the table. AR models such as VQGAN are listed too. Anyway, when you look at VAR, you see that even smaller variants like VARD16 and VARD20 achieve much lower FID scores than the older AR models and do it faster, taking less than a second. This shows VAR is both high quality and efficient. Moving on, Table 2 shows results on the 512 × 512 ImageNet benchmark. VAR gets an FID of 2.63 and generates images in just about a second. Traditional AR models slow down a lot at higher resolutions, while VAR keeps running smoothly. This improvement partly comes from the fact that VAR's runtime complexity grows more slowly compared to AR models that must handle each token in a giant sequence. Check out these comparisons. VAR outperforms diffusion-based transformers too, like DIT and SORA, in both quality and speed. This suggests VAR's approach might be a better fit for large-scale image generation scenarios. VAR also does well against DIT extra large/2 and LDIT-3 billion models, even though it uses fewer parameters. It achieves comparable or better image quality scores and needs fewer training epochs. Plus, it's much faster at inference, about 45 times faster than DIT extra large 2. As model sizes grow, some methods hit scaling walls, but VAR keeps scaling nicely. If you look at Figure 5, you'll see how VAR's test loss and error rates get better as the model size grows. These graphs show near-perfect linear relationships on a log scale, meaning VAR is quite predictable and stable as we scale it up. This stability makes it more attractive for large-scale deployments. They confirm that VAR follows known scaling laws, similar to large language models. They trained various sizes of VAR models, from 18M to 2B parameters, over many epochs and billions of tokens. In all cases, test losses and token error rates consistently follow a power law pattern. In other words, investing more compute or parameters leads to steady improvements. This gives developers a clear roadmap. Want better results? Add more compute, more data, or bigger models, and you'll get predictable gains. It mirrors the strategies used in large language modeling. If you flip the page, you'll see even more detailed scaling laws involving training compute, CMINC minimum. Plots show that as you increase the compute, test loss decreases in a predictable power law fashion. High Pearson correlation coefficients around -0.99 confirm that the patterns hold very tightly. They express these trends in equations. For example, L tilde operator, CMIN, minus 0.13. L tilde operator C min minus 0.13 minus 0.13 means if you boost compute, the test loss drops at a steady rate. The same goes for token error rates, which also follow these neat patterns. This predictability is rare and valuable, making it easier to plan how to improve the model further. As we continue, we see more examples of how scaling compute, CMINC minimum, affects VAR. Test loss and token error rates keep improving as you pour in more computational resources. In section 5.3, they show what happens to generated images as the model grows deeper and trains longer. Look at the examples of 256 times 256 images at different training stages and depths: 6, 16, 26, 30 layers. The images get clearer, more detailed, and more coherent as the model scales up and trains more. This visual evidence aligns with the mathematical scaling laws we've been discussing. Now look at the visuals on the next page. Along the vertical axis, models get bigger. Along the horizontal axis, you increase training compute. The images go from blurry and incomplete to sharper and more realistic. Flamingos and parrots start as vague blobs and become recognizable birds. Cats and dogs evolve from fuzzy shapes to detailed, lifelike animals. This demonstrates that both bigger models and more compute help VAR capture complex patterns. It's a direct, visual confirmation of the power of scaling VAR models in terms of size and training effort. Next, the paper explores VAR's zero-shot capabilities. Without fine-tuning, VAR can do in-painting and out-painting. Check out the examples. The model uses ground truth tokens outside a masked area, then fills in the missing part. It doesn't even need class labels here. They also test class-conditional image editing. Similar to MaskGIT's approach, if you give the model a class label, it can modify the image accordingly. These tasks show VAR's ability to adapt to different contexts and perform well on tasks it wasn't explicitly trained for. Flip to Figure 8 and see how VAR handles these zero-shot tasks. For in-painting, it fills in missing parts so the final image looks natural. For out-painting, it extends the image beyond its original boundaries logically. For class-conditional editing, it can add details that match a given class label. What's notable is that VAR achieves these without specialized training or tinkering. It just uses its learned representations and inference steps. This flexibility suggests that VAR's method of building images scale by scale generalizes well. Now, an ablation study shows what each component of VAR contributes. Replacing a basic AR transformer with VAR alone improves FID from 18.65 down to 5.22, while also cutting inference costs dramatically. Table 3 breaks down the effects of adding adaptive layer normalization, top sampling, and classifier-free guidance, CFG. Each step pushes performance a bit further. By the end, scaling VAR up to 2 billion parameters reduces FID to 1.73, demonstrating the full potential of the approach. This ablation confirms that VAR's design choices are effective and that scalability is key for performance. Continuing the ablation, adding adaptive layer normalization, top-sampling, and CFG keeps improving FID. Normalizing vectors before attention alone drops FID significantly. Overall, VAR is about 45 times faster at inference than its AR counterparts. At a massive scale of 2 billion parameters, FID hits 1.73, a huge improvement from the baseline. They also mention future directions. Improving the VQVAE tokenizer might help VAR perform even better. Integrating text prompts, similar to what large language models do, could lead to a text-to-image generation interface. Finally, moving to 3D pyramids might enable VAR to handle videos, capturing temporal consistency in a way that traditional AR models struggle with. In conclusion, VAR brings a new framework to visual generation, balancing quality, efficiency, and scalability. It beats diffusion models in speed and matches or surpasses them in quality. By scaling up parameters, VAR follows neat power law relationships, making performance improvements predictable. It also excels at zero-shot generalization, opening the door to more flexible visual generation tasks. Check out Figure 9 if you want to see how attention patterns play out. All in all, VAR's structured approach shows how lessons from large language models can apply to computer vision. By building images from coarse to fine, VAR makes generating high-quality, complex images more efficient and versatile. And with that, we conclude this exploration of VAR. From scaling laws to zero-shot capabilities, this method offers a fresh perspective on image generation. It will be interesting to see how this approach evolves and influences future research. Until next time, thanks for diving in.